Okay, so some scheduling matters first before we get started on new material. You'll note that the schedule, I can show you right here, suggests that we should have an exam next week. And so that's what we're going to do. We're going to have exam number 1 on Thursday of next week. And that's going to cover modules 1 through 3. We are starting module 4 today, started it this week. And you're responsible for currently, by the end of this week, by the end of Friday, chapter 4.1 through 4.2. And for next week, 4.3 through 4.5. We're obviously going to do our lecture on 4.1 through 4.2 today. And I'll do a recorded lecture for both sections for October 5th. Okay? And then both sections are going to take this exam at the same time. So therefore, it has to be an online exam. Okay? It'll require going to Canvas, using an honor lock. By the way, who's not got experience with an honor lock on Canvas? Okay, so most people have. So I'm not going to have you do a practice exam. That was pretty much the consensus from the other section as well. I'm not going to have you do a practice exam, but you will need to use Chrome and your honor lock extension and all that good stuff in order to take this exam. I have not made the exam yet, so I can't answer with any authority what kind of questions precisely are going to be on this exam. I can say that there are probably going to be a lot of short answer questions covering topics and ideas that we've looked at in class. Maybe there will be a few questions that you have to work out based on your knowledge of scheduling algorithms or whatever, processes, process control blocks, that kind of stuff. But again, I haven't made this yet. I haven't even started to make it yet. I haven't even looked back to figure out what I want to put on the exam. So I've got a week to do it, and I haven't done it yet. I say next Thursday, I meant next Wednesday, obviously, a week from today. Yeah, so any questions about that I can answer for you?
So there'll be no coding on it?
Yeah, I would say there'd be no coding on it unless it was something brief. I can't even think of what I would put on there for coding. But it won't be anything that you have to compile or run on the server or anything like that. Probably not, but if there is, and just as a general rule, I'll let you use calculators on those exams anyway, so on Canvas exams. So I'll have that as a setting to let you break open a calculator if you want. It'll be closed node, closed book, closed resource. No going online to look up answers. No talking to anybody to look up answers. No looking in your notes to look up answers or anything like that. So, yeah. Yes, sir.
Is it during this time?
Okay, so what I tend to do, and I think I'm going to do it for this class as well, what I tend to do is I tend to open the exam at 8 in the morning and close it at 6:15. So it's a 75-minute exam, so you pick what 75 minutes you want to use to take the exam in. If you want to do it during this time, that's fine. If you want to do it some other time during the day between 8 and 5, that's fine too. But once the clock starts, the 75-minute clock begins. It doesn't end until it elapses or you're done with the exam. All right, what else? So this new material will not be covered on that exam for next week. But this is new material that obviously will get some treatment on an exam the next time we have an exam, so the next time around. Okay? All right, so let's talk about that. Let's talk about this new material. So we know, it's kind of a fundamental fact for us, that processes run simultaneously. Of course, what we mean by running simultaneously is that they take turns having access to the processor. They take turns being processed. And it's the job of the scheduler to determine, which is a part of the operating system, to determine in what order they get access to the processor. We also know, critically, that processes are completely agnostic to the fact that they are not the only process on the machine. Okay? As far as they're concerned, the machine is theirs for the entire time that they are running on the machine, right? Now, if that is the case, then it doesn't really matter. It doesn't really matter. We can just swap in whole memories, whole chunks, whole process control blocks, all back and forth, and there's no shared memory between processes. If that's the case, then we're fine. We've got what we need. Okay, but in the real world, it is often the case that we need processes to share memory. Okay, we need them to be, if they're not aware of each other, they're at least aware of the artifacts produced by one another. Okay? Some process does something, some other process relies on that information for it to do what it needs to do. Okay? Or potentially they have overlapping memory allocations that they need to share in some meaningful way. Okay? So this is memory sharing. And if we're going to have memory sharing, then we need to focus on the idea of concurrency. Okay? Is that a question back there? No? Okay. So we need to focus on the idea of concurrency. What that means is making sure that multiple processes run and share resources. In particular for us today, we're going to focus on memory. Share memory so that they are logically consistent, so that the results are logically consistent for all of the all the processes that are sharing that resource. Okay? Does that make sense? Now, it's the job of the operating system to make sure this happens. Okay? I'm gonna show you some examples of where concurrency can get us in trouble, where we have to have it. Then I'm gonna offer at least one software solution for this, and then we're gonna argue that no software solution solves our problems. Okay, and what we need some kind of operating system fundamental system call, okay, that allows us to do this the way that we want to be able to do it. Okay, so that's kind of the roadmap for where we're going today. All right, so a couple of terms that are important. First off is the notion of a race condition. Okay, that is a state that two or more processes who share memory can get in. Okay, race conditions want to be avoided. Basically, what a race condition says is that the aggregate production of those processes will be different depending on what order those processes run. Okay? We don't know, we cannot know, the process cannot know anyway, when it'll be context switched. It can be context switched at any moment, right? It doesn't know that it's going to be run in order, in some specific order or relative order to other processes. Okay, doesn't know that either. Okay, so let's take a look at an example where a race condition can happen. Let's say I have a circular buffer. Okay, circular buffer. So this would be index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Nothing special about 11. That just happens to be how many I drew. In Tuesday's class, I drew 12. Okay? That makes no difference, right? It's just that it's a circular buffer. And what this circular buffer is it's a print buffer. It's a print buffer. So the way this print buffer works is it has two integer values, two pointers if you prefer, integer values, index values. They are next and open. Okay? And so what the printer does is it looks at this buffer when it gets ready to print something. It looks at this buffer and it says, all right, what's next? And so multiple processes will have filled this up. And what they put in here is they put a file name that they want printed. Okay? So they put a file name in there. And some other guy puts another file name in here. Okay? Some third process puts a file name in here. Then this one gets printed and this one gets printed, and so some more get added, right? So at some arbitrary state, the next might be 2 and the open might be 7. Okay? So next references the index of the next guy to be printed by the printer. Okay? And open references the first place that doesn't have any buffered file names in it. Okay? As it stands right now, this is empty. But in fact, these all have something in them after some amount of use, right? It's just some of this is garbage, and some of it is actual file names that are yet to be printed. So everything from here to here, actually everything from here to here, has file names in it that's meant to be printed. And these are old, this is all old information that's already been printed. Okay, does that make sense? So you can have a situation, yeah, sure, and we'll talk about something close to this later. You can have a situation where the print buffer fills up. So that's a different problem, okay, which we'll talk about in a minute. But effectively, this next and open, they chase each other around this buffer, okay? And why would we want something like this, by the way? Any insight into why we would design a print buffer like this? Are printers fast? No. Slow. They're slow at human scales. They're extremely slow at computer scales. Okay? So we have this print buffer in place so that you don't have to wait, the process, don't have to wait for the printer to be available before you can just say print this and go about your business. Okay? So we hope that this print buffer doesn't fill up. But if it does, we'll have to start doing something else. But let's assume that the printer is fast enough and the print commands are coming in slow enough that there's always space here. Okay? Because this and this, they're always chasing each other around this print buffer. All right, does that make sense? So here's what it looks like when process 1 tries to print. Here's the 3 steps that are required for process 1 to print. It is look up, next, okay? And you're going to store that. No, sorry, look up open. I apologize. Look up open, and you're going to store that. And then put file name at, let's call this X, index X, right? And then you're going to leave it. There's one more step. I'm missing something. Hold on. Oh, yeah, I forgot. Then you're going to increment open. Okay, so you're going to do open plus plus. Okay, does that make sense? So I'm ready to print. I have a file name of a file that I want to print. I look at open. Oh, look, the value of open is 7. Okay, so I take that and I store it right here, right? Then the next thing I'm going to do is I'm going to put my file name at 7, and then I'm going to increment this value to 8. Okay? Any questions about that so far? No? Here's what happens when P2 tries to print. Any idea what the 3 steps are? Look up open. Place your file name in open. And increment open. Okay? These two processes are running simultaneously, okay, at the same time. They're actually taking turns, right, on the processor. So here's what the interleaved execution. Let's call this step 1, step 2, step 3, P2, step 1, step 2, step 3. Here's what happens on the processor. Okay? P1 gets moved from ready to running. And it's the schedule, the vagaries of the scheduler have it running just long enough to do P1.1. Okay? So it looks up, it looks at open and stores it. Okay? Look for the value of open. Okay, I know it's 7. And then context switch. I don't want to use that for a second, but let's do context switch. Okay. Then P2, some other stuff happens. Then P2 gets to go. P2 gets to do P2.1. What does it find for open? Say P2 got to go next. It also found that open was 7. Okay. So currently, P1 is waiting right here. It's ready to go, but it's been context switched, and so it's ready and waiting right here. It thinks open is 7. P2 just looked at it and said, look, open is 7. Okay? So then we get to do the rest of P2, let's say. P2.2. All right, place your file name into 7. All right, so I'm going to use a different color here. So places its file name right there. Okay, then P2.3, okay, increment this value to 8. Now, P1 finally gets released, and its next move is P1.2. Put file name at 7, right? Because it looked up 7. It remembers, yeah, the open place is 7. It doesn't re-look stuff up. It already did that. It found that it was 7. So it writes its file name right here. Do you see a problem with that? Right? What is the problem with that? It overwrote the thing that P2 left behind. Okay? It overwrote P2's file name before the printer, potentially before the printer had a chance to print it. Then it finishes, as you'd expect, P1.3, okay, to increment this to 8. Well, it might even be 9. Who knows? Depends on how increment works. But worst case scenario, we skip 8 until the next time we come around, thus effectively shortening our array, our circular array. This is a race condition, okay? If P1 had been allowed to do these two things before being context switched off, we would have had no problem, okay? If P2 had been, if P2 had also been allowed to do this and P1 to do this before being switched off, we have no problem. But these are separate operations. And we have no idea and the scheduler doesn't have the context for what the processes are doing at any given time, all it knows is time's up, time to switch you off. Okay? Put somebody else back on. So the order in which these operations were interleaved makes a difference as to what the overall output of the two processes in conjunction is. If it happens right, and we get lucky and we have a race condition where this guy wins, quote unquote wins, then we might get lucky and print both files. But if we get unlucky, where we have a race condition where this guy wins and this guy's waiting right here, then we only print one of those files, and P2 never has his file printed. His file was destroyed. The file name was destroyed in the buffer. Okay? Does that make sense? Ask me questions. Anything? So obviously these three instructions in both of these different processes, okay? And they don't have to be the same instruction. They don't have to be executing the same instruction. They just have to be reading and then writing to the same location in memory, okay? This is, and so is this is P1's critical section. You sometimes hear those called critical regions as well. I think your book uses the nomenclature critical section, okay? And this is P2's critical section, okay? We need to make sure that we are careful how we allow the individual elements from critical sections from two simultaneously running processes to interleave, okay? And it's the various interleaving of those statements that can lead to failure, and lead to an unwanted output. Okay? All right, so how do we address this? Well, what we need is mutual exclusion. You guys can't see this, hold on. Mutual exclusion. Okay? You'll hear later on something called a mutex. That is a specific entity that provides mutual exclusion. This is the concept of mutual exclusion, the name of which mutexes are named after. Okay? The idea of mutual exclusion is only one process can be executing in its critical section at a time. Okay? Only one process should be executing inside its critical section at a given time. No two processes, any number of processes may be simultaneously inside their critical section. Likewise, so here, I'm actually giving you 4 rules here. 4 rules. Rule 1. Rule 2, we can't assume anything about number of CPUs or their speeds. Okay? You're like, well, this is not a problem at all. I have a 2-core CPU, right? So, and my multi-core CPUs are set up with memories each has its own memory address space. And so I'll just put one of those on my one CPU and the other on my other CPU. That's great. But now there's two more that come up, and so we've got nothing. How that gets scheduled doesn't help us. It still can have a problem. Okay? We can't make any assumption that no hardware, well, no extra CPUs or faster CPUs are going to save us anyway. Okay, so we're just not even going to consider that. Rule 3, no process running outside its critical section can block other processes. All right, so maybe your immediate response is, yeah, these two processes are problematic because they address the same location in memory. So the easiest way to do this is to just let this one run to its completion before any of the others run to their completion. Right? Just treat them one at a time. That defeats multi-programming. Okay, and that's not what we want. So even any like that's the extreme case, but any case at all where a process running outside of its critical section, there's no reason to let it block any other process. Okay? It can't like save the critical section for itself when it comes back to it. Okay? So that's rule number 3. And then rule number 4, no processes should have to wait forever to enter the critical region. Or critical section. What is it? What do we call it when a single process is continually blocked from getting to the processor? Okay, starvation. So this is no starvation. Okay, this is what is meant by mutual exclusion. Okay. And this is no lockout. Related to this, but not quite exactly the same thing, is this notion of deadlock. And deadlock is actually its own topic for later on, okay? But it's relevant here, so I mention it. We also want to prevent deadlock. And deadlock happens when multiple processes attain resources that other processes are waiting on and are being waited on. Man, that's ham-fisted. I just made that up off the cuff. But the idea is, in order for us to continue, we both need both of these markers. Okay, I take one marker, you take another. We're both waiting on the other marker to be free. We're gonna be waiting for a long time because I'm waiting on you, you're waiting on me. Okay, so that's deadlock. That's the simplest example of deadlock, right? Have you guys ever heard of gridlock? Gridlock. You very rarely get gridlock in Florence, but you do sometimes occasionally get gridlock in Atlanta. Gridlock is where you have an intersection and someone runs a red light and all the cars behind them follow, and then somebody runs over here and these guys are trying to go that way, and these guys are trying to go that way, and so they're all blocked in the middle, right? The resource in question is access to that. And since everybody has somebody they're waiting on and everybody is blocking somebody else, this is deadlock. Except in this case, it's called gridlock because the grid is the streets. Okay? I'm going to hand wave over this for today. Okay? We're not going to worry about deadlock because our examples are simple enough. But in fact, this has its own set of algorithms which are associated with detecting and fixing gridlock in the general case. And we'll probably get to those later on in the semester. Okay? All right, let me show you two processes. You need to see this. So here's process 1 and process 2. Okay? Process 1, let's just say it continuously runs a loop. Process 2 does the same. So these are long-running processes. And somewhere down in here, the critical section of each of those happens. Okay? So how do I make sure that these guys don't enter? And this critical section is made up of multiple lines of code, by the way, right? But just like we said what critical section is before, this would be the example from before where the print spool is happening. The 3 lines for printing are in each of these locations, okay? Something has happened that in this location, you're accessing a shared resource, shared memory, and in this location, you're accessing shared memory. And if these guys enter into these critical sections at the same time, then you have a race condition. And the output, the combined output of these two processes depends upon which one gets to go first. And that's what we want to avoid, okay? So our best way forward is to establish mutual exclusion between those two critical sections, right? We want to make sure that if this guy is executing in his critical section, this guy isn't. And vice versa, if this guy is executing in his critical section, this guy isn't. Okay? So how do we do that? Well, there are a lot of wrong ways to do it, but here's something for us to think about. Let's have 3 variables. Let's call them C1, C2, and weight. Okay? C1, C2, and weight. Doesn't matter what the initial value of weight is, but C1 is going to start off as 0, C2 is going to start off as 0. Okay? When C1 enters its execution, when it goes live, it sets C1 equal to 1. And in the same way, when C2 enters its execution, it sets C2 equal to 1, right? So when these bits are set, it is an indication that the process is alive and running, okay? And about to enter into its critical section, right? So then the third variable rather, is weight, okay? When I'm about to enter my critical section, I set weight equal to my own number, okay? 1. Weight equal to 2, okay? Now, I need to have some kind of structure right here to keep these two things from just running into the critical section. Right? So I'll have a while loop and a while loop here. Okay? While what? Okay? While C2 and will wait equals 1. Or weight equals 1. Okay, let me do this bigger. Under what circumstances is this going to be true? C2 and weight equals 1. This is only going to be true when C2 has done this and this already, and C1 just did this. Okay? So if C2 did this and this, right, then that means that I need to wait on C2 to become 0. Because what process 2 is going to do when it finishes its critical section is it's going to set C2 equal to 0. Okay? And this guy's going to set C1 equal to 0 when he finishes his critical section. Likewise, this is going to be while C1 and weight equals 1. Okay? So I'm going to be inside this while loop. The only time this is going to be true is if weight is 1, which means process 1 has gotten either into its while loop or to the critical section, and I just finished doing this. Okay. So the critical section is right here, right? If I do this, right, and then if I update weight 2 and then this guy gets to go, right, then this is going to make sure that this guy's not in his critical section, and this is going to make sure, sorry, when weight equals not 1, I'm sorry, not 1, but 2. Apologies. This is going to make sure that this guy finishes his critical section, and this is going to make sure that this guy finishes his critical section. Okay, because the very next thing is to say I'm out of my critical section, set C back to 0. I just finished my critical section. What do we do inside these loops? NOP. Just a series of NOPs. What's a NOP? Have you heard of NOPs before? And have you taken any security classes or talked about buffer overflows? Because that's the other place I'm quite sure you would have heard about it. Ever heard of a NOP sled? Is that term familiar to anybody? Nah, what can I do? NOP is an instruction that simply means no operation. Okay? It's a special instruction that means no op. Yeah, no op, NOP. Yep. Instead of noop, it's NOP, right? So this simply means, yeah, you can be running, but all you're going to do is nothing over and over and over and over and over again until this condition is false, which means this guy just did this and jumped back in. And then he finds that he has to wait on you, and wait does nothing over and over and over again whenever he's running until you finish your critical section and do this and jump back in. Okay? Does that make sense? Does this solution work? It does. Is it a good solution? Okay, it's not. Now, why is it not a good solution? At least a couple of reasons. One really big one. Before I do that, though, incidentally, these kind of variables where they flip back and forth, those are called spin locks. Okay, and spin locks, yeah, they have their downfall. And these kind of loops where you repeatedly do nothing over and over again just so that you can not go into your critical section, that's called busy waiting. Okay? So what's the drawback of busy waiting? Okay. Yeah, it's using processor time. So here are the drawbacks for that last example. Busy waiting wastes processor time. Okay. What this does is it's like a hack, right? Because yeah, you can run, but just run a bunch of nothing as long as you are still waiting on that other guy to get out of his critical section. Well, I don't want my processes on the processor wasting the processor time doing a bunch of nothing over and over again, right? I'd much prefer a different solution that keeps that thing from running if it's waiting on the critical section. Okay? You might say, well, we should just let the processes block each other. No. And the reason why is because we don't want processes to be able to block one another. Can you imagine the havoc that would cause if there were a system operation where all you had to do was write a program and be like, block this guy, right? They're agnostic to each other, okay? From the processor's point of view, right? So for the process's point of view, something appears in memory and I use it. That's all that happens. I don't know about that other guy, and I shouldn't know about that other guy, okay? So this is a problem. This busy waiting is a problem. It wastes processor time. We need something else. All right, what about spin locks? This one's maybe not so obvious. When does this guy get to enter his critical section? After this guy finishes his critical section. And when does this guy get to enter his critical section? Oh, yeah, can't see it, sorry. When does this guy get to enter his critical section? After this guy finishes his critical section. And when does this guy get to enter his critical section? After this guy finishes his critical section. Okay? That's enforced, but it's also arbitrary, right? Because spin locks enforce like an extra rule. And that rule is that you have to alternate critical sections, right? I don't necessarily want to do that. I just want to make sure that they stay out of each other, they stay out of the critical section at the same time. Right? A higher priority thing might do its critical section multiple times before this other guy gets to do his critical section. I might like that. I got no problem with that. Right? And so this doesn't break anything, but it's bad for performance and to force that extra rule. And then the third drawback is a bit nitpicky, but once you leave your critical section, there's an extra operation before the other guy gets to go. Okay? So as a technical matter, that breaks rule number 3, which is no process running outside its critical section can block other processes. Okay? So that's 2 really good reasons and 1 kind of nitpicky reason why you don't want to use this approach. Okay? Any questions about this example? Well, let me see what I'm talking about. This example, this one. All right, let's look at a slightly different problem. This is the producer-consumer problem. Okay. Again, I've got maybe a circular. So this kind of looks like our print buffer, right? I've got a circular array, and yeah, even I think that's a terrible drawing. But what are you going to do? Hopefully, it gets the point across. A circular array. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. The producer produces data, and the consumer consumes that same data as input. Okay? I don't know. You can think of probably a billion examples where one process calculates something and puts it over here, and another process picks that up and uses it as its input. Okay, but this is a very common model. Okay. Sometimes this is called the server-client model, incidentally. So what can happen is the producer, right? Again, we've got two values, next and open. And what happens if all of these, if the total number of things in this buffer are equal to the size of the buffer? If the producer has produced enough things so that they're all full, right, then where does it put its next produced item? It can't. The buffer's full. Okay? So we need this notion where the producer stops producing when the buffer is full. Okay? And if next is equal to open, right? If next and open are the same thing, what does that mean? Nope. Do what? We can add something more to it, but it means something else. If next is equal to open. If the next thing that you pick out is also equal to the first place where you're going to put the next thing, what does that mean? No? You have zeros. No, not that you have one spot left, but that you have all the spots left, right? The next thing to pick up is where I'm going to put the next empty thing. Well, the next thing is not there, in other words, right? So that would be that the buffer is empty. And if the buffer is empty, then we don't want to consume out of an empty buffer because there's nothing to consume. Okay? So we need to organize these two processes so that they work together to not do that. Okay? Now, obviously, one way to do this is to use busy waiting again. But a more advanced way to do this is to use two different system calls. One is called sleep, and one is called wake up. Okay? With these system calls, a process that receives a sleep command is put on the blocked list, right? So it goes into the blocked state, processor state, process state. Okay, it's not ready to go. It doesn't leave the blocked list until it receives. So if it receives a wake-up call, if is blocked on sleep, it goes back to ready. Okay? Does that make sense? Here's an example of some code. You guys see that in the back? Good. So here's a producer, here's consumer. you've got an N of 100, that's the size of the buffer, and you've got a count, which keeps track of how many things are in the buffer, how many things have been produced. So when the producer produces, the producer adds 1 to count, and when the consumer consumes, the consumer decreases the value of count by 1. Okay? So item equals produce item, and produce item is some function that generates some item to be put in the buffer. Okay? If count equals n, right? If the number of things in the buffer is equal to the size of the buffer, it means the buffer's full. So before we add that item to the buffer, we tell ourselves sleep. Okay? If that's not true, then we add the item to the buffer, add 1 to count, and then we check to see, hey, if count equals 1, then wake up the consumer. If we added 1 to a buffer and the count is 1, what did that say about the state of the buffer before we added to it? Say that again. We add 1 to the buffer. Every time we add 1 to the buffer, we set count equal to itself plus 1. After we do that, if the count is 1, what did that say about the buffer that we just added to? Before we added to it, how many things were in that buffer? It was empty. Okay? So, in other words, if we just added to an empty buffer, send a wake-up call to the consumer. Okay? Does that make sense? Why? Because the consumer goes to sleep if there's an empty buffer. Right? There's nothing for it to take. There's nothing for it to consume. If it's not an empty buffer, it removes an item, decreases the count, and if the count that now that it's decreased the count and removed an item is equal to n minus 1, right? If we remove 1 from a buffer and we find that the total number of things is n minus 1, what would that say about the state of the buffer we just removed from? It was full. And since we know that producer goes to sleep on a full buffer, if we take 1 out of a full buffer, we should wake up the producer. Looks like I dropped a semicolon there. Remember, we should wake up the producer, right? So this guy is in charge of going to sleep when the buffer's full, and he is woken up just as soon as the buffer becomes not full. And this guy goes to sleep when the buffer's empty, and he is waking up just as soon as there's at least 1 thing in the buffer. When you wake up, do you go immediately to running? No. You go, because there is no path from blocked to running. There's only a path from blocked to ready, right? But worst case at this point, the producer wakes up and produces an item and fills the buffer back up and goes back to sleep, okay? And worst case at this point, the producer gets taken off after having woken up the consumer, which then runs, consumes the 1 thing, and then goes back to sleep. Does that make sense? You understand how this works? Does it work? Does it have a problem? I wouldn't be asking you if it didn't. So it does. Can you see what the problem is? You won't see it by looking at the code. You'll see it by thinking about unfortunate places where these things can be context switched. Okay? And the way it's written is kind of obscures it as well. But there's still a race condition that's present with sleep and wake up calls. Okay? in particular, if we look at this, let's say we're right here, okay? How many instructions is this? Well, it's at least a comparison and a function call, okay? So let's say that the comparison just happened for consumer. And it found that count was equal to 0. So it progresses, and it's just about, its very next move is to call sleep. But right before it calls sleep, it gets context switched off. Okay? When it goes from ready back onto the processor, the next thing it's going to do is call sleep. Right? Does that make sense? That's its next instruction. Its program counter is pointing to call or initialize sleep. Nothing in the world can prevent that from happening. As soon as it wakes up, it's going to do that. Meanwhile, the producer runs, and the producer finds that, hey, look, I just added to an empty buffer, so I should send a wake-up call to the consumer. What's the problem with that? Consumer's not asleep. Consumer is going to go to sleep when it gets back onto the processor, but it got context switched off between here and here. This wake-up call is what's called a missed wake-up. Okay? Let's do that. Missed wake-up, right? Or a dropped wake-up. Is a wake-up that is sent to a process that's not asleep. And since it's not asleep, it's not blocked on the wake-up yet, so it's not released. There's nothing waiting on that wake-up call. Then, at some point in the future, the consumer gets to go again, goes running again, and it goes to sleep. So now, we're in the unfortunate position where the consumer is asleep, but there is not 0 things in the buffer. And the only time that this wake-up call gets made is when there's exactly 1 thing in the buffer, and the next time the producer runs, he's going to add a second thing to the buffer, and then a third, and then a fourth, and then a fifth, and then a sixth, until what? What's eventually going to happen to the producer? Because the consumer's asleep, the producer is the only entity that can tell the consumer to wake up, and he already tried, but that wake-up call got blocked. Now the producer's running, and he's producing things. Is there anything to consume? No? So eventually what's going to happen? He's going to fill it up. He's going to fill it up. And when he does fill it up, he's going to go to sleep. And now both the producer and the consumer are asleep, and that's not good news, right? This is effectively a deadlock. It's a race condition that causes a deadlock. They're both waiting on each other to wake each other up, and neither of them is capable of doing it because they're both blocked. Okay? Now, how likely is that to happen? That depends. It's probably not very likely that you'll get that unlucky, but the fact that you could is a problem, especially if you're running if these things are running for long periods of time, or there's millions of them running all simultaneously. Okay? Does that make sense? It's impossible. It's impossible to get rid of all the race conditions using only software. What we need is we need to be able to do a series of steps and be assured that we're not going to be interrupted while we're doing it. Okay? And that requires the operating system to provide some system calls to us to allow us to do that. Right? We need a system call that allows us to create, to execute critical sections as an atomic unit. Now, do you understand what I mean when I say atomic? goes back to the old days, 50s and 60s, beginning of computers, where, when my dad was growing up, his elementary school teachers told him that the smallest element, the most fundamental element, was the atom. And we know that atoms can be split, and there's stuff that makes up atoms, but they didn't know that back then. So the word atomic, atom, means indivisible. So we need to be able to do those multiple steps in such a way that they can't be divided up. So the operating system needs to provide us some kind of method, some kind of relief, some kind of system call for how to do that. And specifically, what I'm talking about is something called a semaphore. Okay. You guys heard of semaphore before? Either in this context or just outside of this context? Always dangerous when you do an image search on Google in the middle of class. But we're going to go for it, okay? Semaphore. Yeah, that's semaphore. Are these guys right here? You seen that before? Where you have the flags and you can signal over distances depending on like which flag is pointed in which direction and how your arms are oriented. This is an old signaling technique, right? This is called semaphore. Now, what does this have to do with what we're trying to do with our critical sections? Semaphore is where we ask, can I enter this critical section, right? We try to enter, we flag the operating system, can I enter this critical section? And the critical section and the operating system either answers no, somebody's already in this critical section, or no, somebody's already using this resource, or yes, you can enter that critical section because you're the only one that has it right now. Okay? This was invented, incidentally, by Edgars Dijkstra. There's a J in there somewhere. Dijkstra, I think. Dijkstra. You guys heard of Dijkstra before? If you had any of the algorithms classes, you will have had Dijkstra's algorithm. There's at least 2 different ones. Same guy. Okay? This is Dijkstra. He came up with semaphores. Now, Dijkstra was Dutch. And that plays an important role in just a second. Because a semaphore is an integer, or really an integral type, okay, that is non-negative, so only positive, on which there are only 2 operations, which I'll call down and up. But more generally, and I have to look at my notes every time because I always forget, more generally, Dijkstra suggested that they be called P on the semaphore S and V on the semaphore S. Okay? P is short for the Dutch word probeer, and I'm almost certainly butchering it. Probeer means try, I think. Yes. Try. And V is the Dutch word verhoog, which means increment. Okay, so that's where P and V come from, because Dijkstra was famous and he's Dutch. And he invented these. We tend to call them down and up, because down simply means if the semaphore is greater than 0, decrement it, else block on that semaphore. Okay? And this if else happens not as multiple operations, but as a single atomic operation handled at the operating system level. Okay? And some of our reading for next week will reveal some of the hardware stuff that supports this kind of operation, right? Most hardware manufacturers will provide semaphore operations that happen within a single clock cycle, right? So they literally can't be interrupted, okay? And then VS is just add 1 to the semaphore, okay? Now I have to guarantee that if several processes simultaneously invoke PS or VS, the operations will occur sequentially in some arbitrary order. And also, if more than one process is waiting for PS, in other words, if it's on the blocked list waiting for PS, then you're going to arbitrarily pick one whenever VS is run, whenever PS can be executed, right? Maybe I haven't captured this quite right. You block until you can decrement. Okay, does that make sense? So you're ready to go. You need to grasp a semaphore in order to go to complete the rest of your code. If you can't decrement that semaphore because it's already at 0, you block until you can decrement that semaphore. And you can decrement that semaphore whenever anybody runs increment on that semaphore or up on that semaphore, okay? If multiple processes are all waiting on the same semaphore, one of them will be chosen arbitrarily to run, and the others will have to wait until that guy releases that semaphore, okay? Any questions about that? And I have to say again, this happens atomically, okay? That's the whole trick here. That's why it's got to happen at the operating system. The operating system is in charge of saying you do not get interrupted if you are in the middle of trying to either take a semaphore, try on a semaphore, or increment a semaphore. Right? So here's an example, just a simple sketch. Simple sketch for solving the critical section problem with semaphores. You got process P1 and any number of other processes, all of which have a critical section dealing with the same location in memory. All they do, by the way, what's a mutex? So a mutex, sometimes called a binary semaphore, is a special kind of semaphore that begins with a value of 1 and never has more than a value of 1, okay? So what does that mean? That means that only one process can have that semaphore at a time. Okay, does that make sense? This is sometimes called a mutex. So if I try the mutex, if I'm the only one that is about to get it, then I get it, and then I can enter into my critical section. And when I leave my critical section, I release the mutex. And then anybody else who needs to get in their critical section, which is controlled by the same semaphore or mutex, can then run. Okay? This code is underwhelming, but it's great. It's way cleaner than what we had before. And there's no chance that there's a critical section that's not being handled. Okay? Then there's the producer-consumer model solved with semaphores. Here's a semaphore. It has an initial value of 0. Here's another semaphore. It has an initial value of n. Okay? Here's the producer. Here's the consumer. Produce data. Try on E. If you block on E, what does that mean? It means that E is 0. So you can think of E as being the remaining space in the buffer. And you can think of F as being the number of things the number of items currently in the buffer, right? So if you block because there is no space remaining, then you block. You have to wait for VE to happen, right? And VE happens after the consumer removes data from the buffer. If there's room, then you go ahead and place it in the buffer and you increment F, right? And having these things, PF, PE, PF, and VF, VE in reverse order in those two things keeps them from overwriting each other and keeps them from reading from an empty buffer, okay? It eliminates the need for busy waiting. It eliminates spin locks, which means that you don't have the added restriction that they be in their critical sections in alternating fashion. And it also eliminates the lost wake up call because these P and V operations happen atomically. Okay? All right, ask me questions. Yeah.
So what's some of the drawbacks?
One of the drawback of using the semaphores is that you have to use them carefully. And the order in which you use them matters, right? But that's a drawback of programming, you might say, right? If you put PE in both of these places and VF in both of those places, it looks very similar, but it doesn't work, right? The order that you use them in these two different programs matters incredibly, very much, right? And that's just something that you're gonna have to live with. Yeah. At least I don't know of any other way, any better way to do it. There are some more advanced structures like monitors, which you'll read about next time, next week. And we'll talk about it in the recorded lecture from next week. But they're just semaphores with added features. They still have that same drawback. That's a good question, though. Any other questions? Yeah.
Is there a chance for overflow using the semaphore?
No. Because you never place the data in the buffer until you can decrement E, right? Until there's empty space in the array. And there is never empty space in the array if it's full until something gets removed first. Okay? So effectively, if this guy is waiting, because this guy would only be blocked if the buffer were full. And the only way to get it unfull, to not have to wait on this semaphore, is for this to have happened and then this happened. Right? So you're never going to overflow the buffer, and you're never going to try to read from an empty buffer either. Is there an application for security here? Probably not, because buffer overflow, the kind of buffer overflow that causes security issues, happens at a lower level of abstraction. But it's still a very similar problem. It's just semaphores don't address it. I don't know. I'd have to actually think about that. I have to think about that. Answering a question you didn't ask. Anything else? Okay, have I told you about exercise 4 yet? Hopefully you've looked at it. It's about, I've given you some code and it should be altogether easier than the last one. I expect it to be anyway. That's my expectation. There's just not as much to do. But it focuses on having you use threads. It gives you some live action practice with using threads and doing some fun and basic synchronization, although we're not doing anything as advanced as this in the code itself. All right, other than that, exam on Thursday. Be looking for that on Canvas. Opens at 8, closes at 6:15. Right, and then, so I won't see you next week. So let me know if you have any questions, and I'll see you in 2 weeks.